Hello, Aid. I am Rachel Farrell from the Narrative Intelligence Lab at the University of Kentucky, and my work this year is on using narrative planning for belief and intention recognition. But today my co-author will be presenting for me since I just had this baby.
Hello, everyone. This is Stephen Ware of the Department of Computer Science at the University of Kentucky and the director of the Narrative Intelligence Lab. Our lab does a lot of work with narrative planning algorithms. A narrative planner is a single centralized decision maker that coordinates all the agents in a virtual environment like a video game or training simulation. To run, a narrative planner needs an author goal, something that needs to be true by the end of the story, and it needs to know what every agent believes and every agent wants. The output of a narrative planner is what every agent should do in order to appear realistic while still achieving the author's goal. In this project, we looked at the opposite problem of belief and intention recognition. In other words, if we know what every agent did, can we infer what they must have believed and what they must have wanted in order for their actions to make sense? We augment Ramirez and Geffner's influential plan recognition as planning framework with previous work from our lab on narrative planning with beliefs and intentions. The main difference between these two bodies of work is that traditional plan recognition has focused on the observable features of agents and their environments, and assumes that rational agents are attempting to form optimal plans. In this work, we focus on unobservable mental properties of agents, namely their beliefs and intentions, and we assume that agents will act believably, even if not optimally. For example, when agents hold wrong beliefs, we expect them to act on those beliefs, even if this would result in a suboptimal plan. Let's consider an example. Imagine 3 rooms with a robot in each room and a handful of items that can be picked up and given away. We observe the red robot pick up the flower and walk to the room on the right. Based on these observed actions, what can we infer about Red's beliefs and intentions? Plan recognition as planning works by compiling the observed actions into the problem. Let's say we've observed an agent taking 2 actions, and we have 3 candidate goals. We want to know which of these goals is the agent's actual goal. Every planning action has a precondition that must be true before it can happen, and an effect that changes the world in some way. The PRP framework generates a new predicate that's not used anywhere else in the problem, and adds that predicate to each of the goals, and also to the effect of the last observed action. Then we generate another unique predicate, add it to the precondition of the last observed action, and the effect of the second to last observed action, and so on for all of the observed actions. In this new version of the problem, it is impossible to achieve the goal without taking all of the observed actions. To decide which of the candidate goals the agent is most likely trying to achieve, we run the planner for each of these 3 modified problems. Remember that the observed actions have to occur, and the planner will fill in any other actions needed to achieve that goal. The intuition behind the PRP framework is that the easier it is to build a plan that contains all of the observed actions, the more likely that goal is to be the agent's true goal. We apply the same intuition to the narrative plan recognition problem. We've observed some actions happening, and we have some candidate sets of beliefs and intentions. For each of those sets, the easier it is to find a believable plan using them, the more likely those beliefs and intentions are to be the true ones. Let's return to our example. Say the red robot is in love with one of the others. The purple robot on the left loves flowers, while the yellow robot on the right loves candy. We've observed the red robot picking up the flower and walking to the room on the right. What can we conclude about Red's beliefs and intentions? Well, there are at least 2 reasonable conclusions. The first is that Red is in love with yellow but mistakenly believes that the yellow robot wants flowers. Another equally reasonable conclusion is that Red is in love with purple. Red accurately knows that purple wants flowers, but Red is mistaken about purple's location. This example highlights some of the challenges of belief and intention recognition. First, we can't really separate it into 2 different problems because beliefs and intentions interact. Second, there are often several explanations for the same series of actions. And third, even though in traditional plan recognition the problem becomes trivial once you've observed every single action, that's no longer true for us. Remember, agents can form plans, begin to execute those plans, realize something is wrong, and abandon their plan. That means there are some intended but not executed actions that are an important part of the problem, but remain unobserved. Therefore, even if you observe every single action that an agent takes, belief and intention recognition is still not a trivial problem. Our algorithm attempts to account for these challenges. It takes as input the observable features or physical configuration of the initial state, the actions that we know agents have taken. It can also optionally include the author's goal, if that is known, and the beliefs and intentions of any agents that are known. The more information, the better. And the last element of input is sets of beliefs and intentions, which could potentially explain agent behavior. The process is similar to PRP. We compile the observed actions into the problem and run the narrative planner for every candidate set of beliefs and intentions. The narrative planner not only generates a sequence of actions to achieve the author goal, filling in missing actions as necessary, it also makes a best effort to explain every action in terms of the beliefs and intentions of the characters who take them. It's possible that actions are explained by intended but not executed actions. The output of the algorithm is every set of beliefs and intentions that is able to maximize the number of observed actions that were explained, while introducing the fewest unexplained actions in order to generate those explanations. When the algorithm returns more than one set of beliefs and intentions as reasonable, how we break ties depends a lot on the application. For example, we might want to use Occam's razor and assume that the candidate with the fewest wrong beliefs and intentions makes the most sense. But if we're building an intelligent tutoring system, then we might want to assume that the player has the most wrong beliefs just in case. Likewise, if agents are trying to recognize one another's behavior, agents might want to be either optimistic or pessimistic about whether other agents will be friendly, depending on the application and whether or not their plans need to be robust to conflicts with others. We evaluated our approach to belief and intention recognition in two ways. In the theoretical evaluation, the ground truth about what every agent actually believed and wanted was known because we generated the problems ourselves. We also did a practical evaluation where we compare the performance of our algorithm against human raters performing the same task. The planning domain used for our theoretical evaluation is a parameterizable version of the robot example given earlier. There's a grid of rooms inhabited by agents with items distributed throughout. Agents are trying to woo one another by giving each other gifts. They can walk between rooms, pick up and drop items, give items to one another, and tell each other what items they want, which can be a lie. The initial locations of agents and items, as well as who loves who, can be randomized. Agents can have wrong beliefs about where items are located, where agents are located, and what other agents want. We designed this domain to have many of the properties that we encounter when designing narrative planning problems, including movement between locations, interactions with items and agents, communication, conflict, and cooperation. We randomly generated several thousand example problems in this domain and then applied our algorithm. We considered 5 different ways to reduce the ground truth, in other words, the sequence of actions that actually happened, down to a set of observations. The first and simplest way is simply to use every single action as an observed action. Remember that in this problem, that still does not make it trivial to recognize beliefs and intentions because some things could be explained by actions that agents intended to take but never actually took. We also preserve only the first 2/3 and the first 1/3 of actions. This is equivalent to trying to recognize what's going to happen before the simulation finishes. We also considered 2 other methods. One was to observe only the actions that occur in a specific room, and the other was to observe only the actions that are observed by one specific agent. Here's a visualization of our results. On the x-axis, we have the number of actions that the belief and intention recognition algorithm has to observe when making its decisions. The more actions, the more information it has. On the y-axis is the number of sets of beliefs and intentions that got labeled as reasonable to explain those actions. Each line represents a different ablation method, with this line representing the overall average. All of these lines trend downwards, which is what we were expecting. In other words, as the algorithm has more information to work with, it's able to rule out more sets of beliefs and intentions as reasonable. However, even when the algorithm has all 5 actions to observe, on average, there are still about 2 sets of beliefs and intentions that can be used to explain those actions out of the set of 10. These results are a valuable sanity check, but we also wanted to evaluate our algorithm in a practical setting. We applied our belief and intention recognition technique to 33 examples of human players participating in our virtual reality police use of force de-escalation training simulation. In this case, the ground truth is not known, meaning that we don't know what our players actually believed and intended. We compiled 48 reasonable sets of beliefs and intentions that different kinds of players might have, and then we trained human raters to watch the videos of those play sessions and label what they believed the players' beliefs and intentions to be. Then we compared the output of our algorithm to the output of those human raters. The simulation is designed to teach a lesson advanced by the Police Executive Research Forum that officers should keep distance and cover between themselves and suspects in order to buy time to de-escalate a potentially violent situation. Let's consider an example session from our training simulation. If we only observe the first action, it suggests that either the officer does not understand the importance of keeping their distance, or they're intentionally trying to provoke the suspect. But if we observe the third action, it suggests the former. The officer did want the suspect to surrender, they just didn't understand the importance of keeping their distance. Planning algorithms are deterministic, which means that repeating an action has no effect. This is different from the real world, but unfortunately our narrative planner was only able to explain one of these two copies of this action. This is a problem we hope to address in future work. Finally, if we consider these two actions, they suggest that the officer did not realize they could retreat to behind the police car to keep cover between themselves and the suspect. This is a common misconception that was identified by the Police Executive Research Forum. Ideally, this officer would then replay the simulation, learn the importance of distance and cover, and earn a better score. We looked at results in two different ways. For 12 of the 33 sequences, 2/3 of raters agreed on every belief and intention. In 8 of those cases, our algorithm recognized that set of beliefs and intentions as valid. These are decent results given that the chance of guessing correctly is only about 17%. Another way to look at these results is that we considered all 33 sequences, and when raters disagreed about a particular belief or intention, we considered any value for it to be correct. Our algorithm returned at least one correct set of beliefs and intentions, 20 out of 33 times. These are encouraging results given that the chance of guessing correctly is only about 1%. These initial results suggest that narrative planners can be used to infer the beliefs and intentions of agents as we observe their behavior. There are many possible applications for this work, including recognizing what players believe and what they want in an interactive scenario. This will be especially helpful for intelligent tutoring systems like the de-escalation training simulation we developed. There are also applications for helping intelligence analysts make sense of global events as they observe them. Finally, we'd like to thank the U.S. Department of Defense for partially funding this research.